Hello and welcome to this video about heterocyclic chemistry. Here we'll look at some key concepts which are important to this course. You should have encountered these concepts previously and be comfortable with them before going through the rest of these videos. If not, it's a good idea to go back and look through some of your previous notes. To start off with, we're going to remind ourselves about curly arrows. Curly arrows are the most important part of our mechanisms, and they represent the movement of two electrons. So that means that they should flow starting from somewhere that has a source of electrons, and they should end up somewhere where there is a sink of electrons. For example, from a negative charge, or a lone pair, or a filled orbital, to a positive charge, an empty orbital, or an anti-bonding orbital. If we're breaking a bond, it's important that we have a good leaving group, and a good leaving group can be characterized by something that is acidic. For example, Cl- is a good leaving group because HCl is an acidic molecule. If we look at this more slowly, most importantly, our curly arrows, especially our curly arrows with two Looking at this more slowly, our curly arrows with a double head represent two electrons moving. This means that they should start off somewhere where there are two electrons. And they should move somewhere where there is some kind of positive charge. So, where do we find electrons? Well, in a negative charge there are two electrons, so we can draw our arrow coming from the minus of a negative charge. In lone pairs there are two electrons, so we can draw our arrows coming from the lone pair. And in filled bonds we have electrons, so here the pi bond can use its two electrons to attack, and therefore we can draw an arrow coming from there. Each one can attack the corresponding positive charge, so we can have arrows attacking a positive charge on a carbocation. We can have electrons attacking an empty orbital, for example on a boron atom. And we can have the breaking of a bond. So in a good electrophile, like a carbonyl, we have breaking of a bond. Or if we've got a good leaving group, like chloride, we can draw the arrows breaking the bond and leaving the chloride minus anion. A lot of the chemistry we'll look at involves the chemistry of aromatic rings. The two most important reactions in aromatic chemistry are nucleophilic aromatic substitution and electrophilic aromatic substitution. In nucleophilic aromatic substitution, electron-poor rings, for example, those with nitro groups, or ketones, or sulfonyl groups, or nitriles, undergo nucleophilic substitution if there's a good leaving group, for example, a chloride, bromide, iodide, or fluorine. The electronegativity of the leaving group further accelerates the reaction, which is why the substitution of fluorine is the fastest of all of the reactions, because it is the most electronegative. Our mechanism involves the attack of a nucleophile. Here we have OR- to the aromatic system. This breaks aromaticity but leaves the negative charge adjacent to the nitro group. And then aromaticity is restored when the charge comes back through and kicks out the chloride leaving group. We can look at this again more slowly. If we start off with an aromatic system with some kind of electron poor group, such as a nitro group, that is substituted with a leaving group, for example a chloride, then we have a nucleophile such as methoxide. The negative charge, remembering that our arrow represents the movement of two electrons, so we can draw it coming from the negative charge. We can then push the arrows round so that the resulting negative charge is on the carbon next to the nitro group. This has broken the aromatic system, but we have that negative charge on a carbon next to the nitro group, and we can see how the nitro group is good at stabilizing that charge over all of the atoms, so the negative charge is spread out on that carbon, but then also on the adjacent oxygen, so we can draw a resonance form whereby the negative charge is on the oxygen atom, but the final step is to restore aromaticity, and we do that by pushing the electrons back around the aromatic ring and kicking out our good leaving group, which is the chloride anion. This means that we swap our leaving group for our nucleophile, so it's a nucleophilic substitution, and on an aromatic ring. The opposite to nucleophilic aromatic substitution is electrophilic aromatic substitution. Here, the pi cloud of the aromatic ring is a nucleophile, but because for this reaction we need to break the aromaticity in the system, that means we need a very good electrophile. Normally, we have electrophiles that possess a permanent positive charge. In this process, we remember that the different groups around the ring are really important in determining selectivity. Electron donating groups, such as an amine or an alcohol or an alkyl group, activating, they funnel electrons into the ring, and then they donate ortho or para to their position. Electron withdrawing groups deactivate the ring, they take electron density out of the ring, and they direct to meta. Halides have a bit of both, whereby they're deactivating because they're electronegative, but then they're ortho and para directing because their lone pairs donate into the ring. So in the case of nitration, what we have is sulfuric acid and nitric acid, and sulfuric acid is a stronger acid than nitric acid, and so it dehydrates the nitric acid to form the nitronium cation. Because in this example we have nitrobenzene, we get attack of the aromatic ring onto the positive charge on that nitrogen atom in such a way that that positive charge stays furthest away from the nitro group. So the two electron pore centers are not on the same atom. Therefore, we end up with a nitro group at the meta position. But in this step, we've broken the aromaticity, but we can regain that aromaticity by losing H+, and that gives us our product. Looking at this slowly with a slightly different substrate, again for nitration, we start off with nitric acid, and we have a stronger acid, so sulfuric acid, and the sulfuric acid is able to dehydrate the nitric acid. It's able to protonate the OH group of the nitric acid, which makes it leave to give the nitronium cation NO2+. The resulting negative charge is stabilized on a very electron withdrawing HSO4-. Now, because we have such an activated electrophile, we can use the electron density of the ring. Here, we've got electron donating methoxy group, and so we can see we can push the lone pair from the oxygen round the ring and have attack from the 4 position or the para position onto that nitronium cation. This breaks the aromaticity of the ring, but we can restore that aromaticity by losing a proton and regaining the aromaticity by quenching that positive charge. We could have also pushed the arrows the other way and get nitration at the ortho position or the 2 position. One reaction that's going to be very important in the synthesis of heterocycles is the formation of enenes and enamines. So if we have an electrophilic carbonyl species and a nucleophilic amine, they will condense. The nitrogen will attack the ketone to form an iminium species, this species with a positive charge on the nitrogen atom. And if the R group on our amine is an H, i.e. a primary amine nucleophile, we'll get deprotonation to give the imine. And if it is not an H, then we'll get deprotonation of the carbon to give the corresponding enamine. This whole process is reversible, and it's very important in many of the syntheses we will see later on. Looking at this more slowly, we have our carbonyl species. The carbonyl is a very good electrophile. The electronegative oxygen atom polarizes the double bond. And we have an amine. The amine is a very good nucleophile because of that high energy lone pair. So, our nucleophile amine can attack the carbonyl, break the CO double bond. The resulting O is quenched with an H. At this stage, our nitrogen lone pair comes back in again and pushes out the OH minus leaving group. So we have N plus OH minus. Now at this stage, if the N plus, the iminium species, has a hydrogen on it, we can simply remove that hydrogen, and that gives us the imine product. Alternatively, if it is not the primary amine, i.e. the R is not an H, then we can't deprotonate the iminium, so we deprotonate the carbon instead. And this gives us a neutral species, and that's the enamine, so a double bond next to an amine. The imine is a very good electrophile, and the enamine is a very good nucleophile, and this is how they're important for synthesis. Okay, so we've had a quick look at 4 key areas which are essential to the rest of this course. First of all, we've revisited curly arrows, the movement of 2 electrons, and we've seen what we need to be able to draw good quality curly arrows. Then we looked at the reactions of aromatic systems, specifically nucleophilic aromatic substitution of electron-poor aromatic systems, and electrophilic aromatic substitution. Finally, we had a look at enamine and imine formation, where we can take an amine and a carbonyl, and they will condense to give us the enamine or imine, depending on the type of amine that we start with. Thanks for watching, and I'll see you next time.